Okay, so I'm just going to go over the motion map pages with you guys. So on Friday, we did the first one together. Right? You guys ready to go?
Yeah.
Okay. So on Friday, we did the first one together, figured out how to take our position versus time data and convert that to both the motion map and to a description of the motion of the object in words. For number 2, we started this out a little bit and started to label some of these dots, but didn't do either of the other things. So I like to go from the motion map to the position versus time graph. And first thing, I like to number all these so I know what second goes with each one. So now I know the times for each of these, and then all I have to do is read the data. This says that at 0 seconds, I'm at 5 meters. Grab a color. So I'm going to be at 5 meters. At 1 second, I'm going to be at 4 meters. So I'm just going to read these. At 2 seconds, I'm at 3 meters. 4, 5, and 6 seconds, I'm at 2 meters. So here's my time, 4, 5, 6. I didn't miss 3. 3, 4, and 5. 3, 4, and 5, I'm at 2 meters. At 6 seconds, I'm at 1 meter. 7 seconds, I'm at 0. 8, 9, also at 0. 10 is at 2 meters. And 11 is up to 4 meters. How'd you guys do? Is it okay? This part here is pretty steep. I'm just connecting these with a line. Makes it a little bit easier to see. So then the motion of my object. I'm going to say that my object starts at 5 meters. And then my object moves which direction, positive or negative? Our object's going to move in the negative direction because our position's getting smaller. We can say how long for 1, 2, 3 seconds. We can also say how fast it's going. Because we're moving 1, 2, 3 meters in 1, 2, 3 seconds. So that's going to be 1 meter per second. Then our object is still for 2 seconds. Moves in the negative direction for 2 seconds. Distance of 2 meters. So our speed is 1 meter per second. Our object rests for 2 seconds between 7 and 9. And then moves in the positive direction for 2 seconds over 4 meters. So there our speed is 2 meters per second. All right, does anybody have any questions about number 2? Okay. So then on the back, on page 6, we have a problem where we've got 2 cyclists, cyclist A and cyclist B, and I don't know, I like to imagine that they're racing, but who knows. We only have 1 point of time, and that's at 5 seconds, and we don't have any distances marked on here. So a lot of what we talk about is going to have to be relative. It's just going to have to be comparing it to what's happening to the other racer. So here it says, do the cyclists start at the same point? How do you know? If not, which one is ahead? So no, they don't start at the same point, because here, when time is presumably 0, we've got cyclist A starting at a different position than cyclist B is. Right? Cyclist B and cyclist A do not start at the same point. The one that's ahead, the one that's farther distance from that point, is going to be cyclist B. How do we know? Because their intercepts are different. B is ahead. At 7 seconds, which cyclist is ahead? How do you know? All right, well, we don't really know where 7's going to be, but we can make some inferences about that, right? If we've got 0 and 5, then we can start to think about, okay, well, how much is 1 second worth on the scale? So I just drew some marks there. If I try to estimate where 7 should be, I would estimate about here. In some ways, it doesn't matter because the question is just asking us what happens after 5 seconds. So we can tell that anything over here is after 5 seconds. So at t equals 7 seconds, which one is ahead? The one that's traveled the furthest distance from our 0 point, which is going to be A. How do we know? Because the y value for A is bigger than the y value for B. And that y value, again, is distance, which in physics we usually write as x. How do you guys feel about that? Have you considered that before with a graph like this? Is that we do this strange thing in physics where we have an x-axis that is time, and then our y-axis is distance, and we use the symbol x for that. So just make sure that when you're looking at graphs that you're being consistent with what your markings are. So I put y value here, but there's nothing that's labeled y on this graph. But it is labeled x meters. Just like we have t seconds, time seconds, position in meters. And you'll see position as x over and over again in this class. All right, it asks us next, which cyclist is traveling faster at 3 seconds? So 3 seconds, again, is going to be on the left side of the 5. Who's faster? How do we know? Well, the one that's traveling fastest is going to be the one that has the steepest slope. So who's traveled the farthest distance at that time? Because the time is the same. So really all we need to do is figure out who's traveled more distance. So if we look at this, the distance traveled by A is going to be this much. The distance traveled by B, see at 3 seconds, this probably got picked because that was the starting location for B. Has B traveled as far as A? There's B's distance, and there's A's distance. B's traveled much farther. Sorry, B has not traveled as far. So A has probably got a higher velocity. Does A have the steeper slope? Can we tell by looking at that? Yeah, we can see that. Are their velocities equal at any time? Ooh, what's velocity? Have you guys used the word velocity before? Okay, so this is going to be your first, our very first discussion about velocity. We'll make it really simple. It's like speed, but with direction. Do they have the same direction? Yeah. What about their speeds? Are their speeds the same? Yeah, I'm seeing lots of you guys shake your heads no. Their speeds aren't the same. If they were, their speeds would have the same slope. So I'm going to say, velocities are never equal because the slopes are never equal. What happened at the intersection of A and B? What ideas did you guys have?
I said at the intercept, I said A passes B.
Yeah. Well, if you've got two objects that are in the same position at the same time, what does that tell us? They're passing. Hopefully they didn't run into each other, right? Thank you. What do you think would be different on our graph if they actually ran into each other? They would both stop. Yeah. they wouldn't go anywhere. So we'll say they passed each other safely, hopefully. Okay. Down at the bottom is our motion map, and this is the trickiest part. Do you guys find this tricky? Yeah. It is admittedly tricky. So I'm going to do 2 different colors here. See if these show up. All right, so I'm going to start by doing one of these. I'm going to start with cyclist A. Can you guys see that? Or is that too? I need to get my other pen to bring them in. What nuclear pink? I can see that really good, and it's not good on camera. Here we go. Let's go big or go home time. I don't know. Are any of those good? All right, if I'm going to draw what happens to A. So I do know that at 5 seconds they run into each other, and that's all the information that I have to go on. I also know that B starts ahead of A, but doesn't start at that 5-second point. So what I know, is that bad, or can you guys see that? That's bad, isn't it? You guys can tell me it's bad. Dr. O'Malley, it's not good enough. That's a little better. I'm gonna just say A starts at 0 because that's what our graph says. Starts at 0 and then moves for 5 seconds. 1, 2, 3, 4, 5. So if A moves for 5 seconds, that means there has to be 6 dots. I'm going to draw my arrows too. And there's nothing in this data that says that this is wrong, right? All I needed to do was start at 0 meters, and then I needed to travel for at least 5 seconds. What's going to happen at 5 seconds? We already said it, right? It's going to run. It's like a low rumble. All right, B. I'm going to do B in blue. I know that A and B are at the same location at 5 seconds. I also know that B did not start at 0. B started away from 0. So I know that if this is T equals 0, T equals 1, and I'm putting them on purpose on the top because I'm going to put another row for B down here. And I don't want to confuse them. 2 seconds. T equals 3, T equals 4, T equals 5. I know that for B, my 6th dot has to be at the same place that my 5th one is for A. I also know, you guys see this? We had decided that the location earlier, that the location where B started was the position that A was at after 1, 2, 3 seconds. So if I come down here, I'm going to go where I put A at 3 seconds, and that's where I'm going to put my first dot for B. But now I have to get a whole bunch of dots in between these two, right? I have 6 dots for 5 seconds. 1, 2, 3, 4, 5, 6. So I need to put 4 more dots in between those two. So I'm just going to do the best that I can. My arrows go halfway between them. And we can tell from looking at our motion map that B is going slower because it has shorter arrows. Right, he's going lots slower. A traveled a lot of distance. We can figure out what happens after that point by continuing those points. So I'm going to label this one T equals 5, but then I could keep going with this past that point. And if I kept A going for 3 more seconds, it's going to look like this. How'd you guys do on that? Yeah. We'll get a little more practice. This is kind of, in terms of motion maps, this is kind of tricky, right? Because you guys were trying to make some inferences about about a position versus time graph that had very little data. Okay. Next one, we have a new position versus time graph for cyclists A and B. What changed here between the previous graph and the new graph? Did B change at all? No, just A. How did A change? There was one thing that happened to A. It changed direction. Yeah. And because it changed direction, now it has a negative slope. So now they're going the opposite directions of each other. It says, how does the motion of cyclist A compared to that of A in question 3? We already said change directions. Doesn't say, how did you know? How does cyclist B compare to that? Doesn't change. Which cyclist has the greater speed? What do you guys think? Biggest speed. Meters per second. A does. A changed direction, but not speed, right? Still A. How do you know? Steeper slope. So then what's happening at the intersection of A and B? Is that going to change from before? That's not going to change from before. That's still where they passed each other, right? So A and B pass each other. Which one has traveled farthest in the first 5 seconds? So here's how far B traveled, and here's how far A traveled. Who traveled farther? A did, right? A. Because they did. I'm going to write because the change in XM was greater. All right, and then draw a motion map. So this is going to look really similar to the one we did before, which we can still see down there. This is unanticipated, but maybe I can just, can I copy it? Nah, it's going in the wrong direction. You know what I could copy? I could copy the purple one. Because it changed direction, right? So it's just on the other side of the page now. But B, I have to mess with that. So this one's going to be, come on. This one's t equals 0. This dot is t equals 5. I started farther away from 0 and moved back towards 0 with this one. For B, B is going to be in the same place that A was, but it started, we decided before it started at 2 meters, 3 meters? 3 meters. Put him there. I'll trace over it with black. It'll make it a little bit easier to see. So here's A, moving in the negative direction, but at the same speed that we did in the first problem. There's A. B is going to go the other way. They're so close together, it's tricky. So at 5 seconds, those two are at the same point. That's where they pass each other. What questions do you guys have about that one? Any questions? guys ever walk a dog? Wonder who travels more distance, the dog or the person? Always the dog, right? People don't run around like dogs do. So here we've got an overhead picture of Dorothy and Toto walking along the yellow brick road. Dorothy is very intentionally walking along a straight path. The dog, Toto, you guys know Toto, right? Yeah. Toto is running around in circles, around all kinds of things. What's that look like? I think it's a tree, but it doesn't look like a tree. Maybe it's a fire hydrant. So Toto's going to run circles around things. If we were to try to figure out from start to finish who went further, what do you guys think? Dorothy traveled from this point to this point, and Toto went from points that are within that. Does that mean Toto went less distance? No, we could measure this path, right? We could actually track how many steps Toto took and use that to measure how far he traveled. And we would say that Toto traveled farther because the distance of that dashed line is longer than the solid line. Okay, so there's two different ways that we can keep track of how far something has moved, right? We might not care that he ran around all these things. If we're only interested in the endpoints, who traveled farther? If we only care about the start and the finish, Dorothy traveled farther. If we care about the path, can't spell, farther. Okay, if we care about the path, do you guys see the difference between those two? If we care about the path, Toto went farther. If we only care about the start and the finish, Dorothy traveled farther. Okay, you guys have any questions about that page? No? Okay. I'm going to stop.